that's been built for the old networking stack. What does all of this change mean to you? In other words, how do you move from the old world to the new world? This is something that we had to give quite a lot of thought to, because out of the gate, we wanted as much capability as there was on Windows XP SP2 in terms of securing the system to exist on Windows Vista and more. The basic problem I'm asking here is the following. When you think about what you're doing with security solutions, what you're doing is you're looking at the runtime state of a system, the operations that are going on, and you're enforcing policy decisions around those. So for instance, this particular application cannot connect to the following website, or the following words are considered bad and they should be edited out of websites, for a parental control application. And in the Windows XP stack, it was fairly difficult to do that. You had to plug in kind of blind at these gross interfaces. Either you could look at the packets that are getting emitted by the networking stack, or you could plug into the TDI interface or have a WinSock layer service provider and try and kind of divine or intuit what's happening inside the stack from outside the stack. So that's this picture. So this is what you used to have to do, and you'd basically be trying to figure out this state machine, which is a fairly rich state machine and complicated, from the packets that get emitted or the API implications that you see. That tends to limit what you can do in terms of securing the system. The key observations I went into redesigning the networking stack were that if you want to enable people to build security and extend the security capabilities of the networking stack, you have to give them visibility into what the stack is doing. You have to give them ways to directly control the behavior of the stack. So, for instance, reach into a state machine and say, no, this transition is not allowed because of the following reason. And then finally, you have to decouple all of this. You have to decouple the ability to control the stack's behavior from the stack itself, so that long after we ship, the behavior of the stack can continuously evolve in response to threats. That's the way that you build a networking stack that can keep pace with security threats without being bound to binary releases of code from the operating system vendor. The result of that is the approach that we took in the NetIO stack. The basic way to think about the approach that we took is that we took anything that we could think of that seemed like it was a policy decision that we might be making inside the stack. We tried to externalize that and provide interfaces that would allow an external component to tell us what to do in that situation. I can show you what that actually looks like in the debugger. If I dump out a set of routines that start with, for instance, the prefix inet inspect, what these are essentially routines that are implemented in the stack that are callouts that we invoke to ask someone to tell us what to do. So for instance, if someone tries to, say, acquire a port, so a port assignment, that's something that we will actually turn around and ask an external security component, can the following process acquire the following port that it's trying to take? If there's no security component installed, then we'll just do whatever the default behavior is. But across the board, at every layer in the stack, we're continuously asking for permission to do everything that an application is trying to get the networking stack to do. So you can think of that as decoupling the state machine from the policy that's behind the state machine. And then what we did is we wrapped it up, we took that capability and we wrapped it up in what we call the Windows filtering platform. The Windows filtering platform is the way to think. I'll give you a pictorial way to think about it and then kind of a more concrete way to think about it. If this is the networking stack, so kind of you think of a flat plane, RPC on top of Windows sockets, and then you have TCP and UDP and IPv4 and v6 on top of that. This is kind of how the Windows filtering platform changes that picture. This will be a little hard to see because the colors are light, but you can see that from the stack there are callouts that are flowing through things like secure sockets, application layer enforcement, and these built-in components that know about networking policy. And then as a second level, you have a base filtering engine and a core filtering engine that exist to help third-party components plug into this infrastructure and also influence what's happening inside the stack. The final step is things like IPsec policy, firewall, and so forth. They are the ones that actually implement customized policy around what the networking stack does. So So a more concrete look at what was in the picture. So you have the core stack and built-in policy-related components like application layer enforcement that keeps track of processes, threads, and so forth, and what the operations are at the application layer. We've built a stream inspection module that allows a third-party component to subscribe to a particular TCP stream. So for instance, if you want to edit the contents of the stream or just inspect, you can actually take out bytes from the TCP data stream and put in replacement bytes, and the stack will take care of fixing up any sequence numbers and so forth to make it look transparent to the application. And then finally, IPsec has its own filtering logic around when IPsec is negotiated between various machines and how policy arbitration happens. So those are the elements of the built-in elements. And then we have the core filtering engine and filtering callouts. The filtering callouts you can think of as components like antivirus, firewall components, parental controls that basically provide filters saying, I'm interested in these kinds of operations, and then the stack makes sure that they get to see those operations and that they can say, for instance, block those operations or suspend them while they go off to user mode to get permission, and so on and so forth. So the way that we've broken up everything that happens inside the networking stack is we've defined the notion of layers. So we have layers all the way from RPC that let an application plug into the RPC engine itself and understand what it's doing at that level and control operations at the RPC level. You can also plug into operations at the socket level, things like listens, accepting connections, establishing connections, and assigning ports. You can plug into the data stream. You can plug into the inbound and outbound messages that get emitted as the result of all of these state machines or as the result of applications doing I/O. And then finally, control traffic can also be inspected through the filtering platform. So I'm going to take this question. We have a lot of slides to get through, so if it's not a deep question where something just doesn't make sense, try and defer it to the end. I'll also be in the booth afterwards. But your question? I'll talk a little bit about that towards the end. So what does this enable? The biggest thing is extensibility. The other thing is transparency, because by exposing the operations inside the stack, it gives you a much better feel for what's happening. I mean, you shouldn't be wondering how Microsoft implemented this algorithm inside the TCP/IP stack. We'll just tell you what the state machine is, and then you can participate in that state machine too. And then finally, the fact that we've built this tightly into the stack means that we can do all of this and still maintain really good performance, as opposed to what you would get if you had a third-party kind of plugging in on the peripheries of the subsystem. So that's to give you an idea of how we approach the question of how do we make sure that the security profile of the system can continuously evolve. We have a beta program around with the Windows filtering platform, and we have most of the leading vendors are already aware of this. This is also a platform that can be used for developing your tools and doing research if you want to understand better how networking works, or if you have particular ideas for how to change the behavior of a networking stack. What we've essentially done is we've tried to build the basic scaffolding that anyone would need by just using Windows Vista in this mode, and we're basically giving you a stack that you can customize and you can make it behave more, for the most part, how you want without having to write all the code. So that's the platform piece of what we've done and what we've done to try and make it easy to extend. I'll switch now and I'll talk about what we've done for applications. So one of the biggest problems that network applications have is figuring out when am I connected to the network so I can go off and use some website. And we've put in some capabilities in Windows Vista to actually make that quite a bit easier. So the problem is, how do you detect for a particular internet connection that it's actually the internet? There's a component called network location awareness, which has a couple of algorithms built in to try and answer that problem. So the first basic idea is that imagine you have a PC that's plugged in. It has multiple connections, a wired connection and a wireless connection, and you want to figure out which connection is good for use on the internet. In this case, I've shown a wireless hotspot, which won't get me to the internet because it's just spoofing DNS queries. The basic approach to detect this fact is to send a query for a known DNS name, and for instance, for a text record, and look at the response. If the response is what you expect, then you can conclude that it's the internet. And you can take this further, and actually customize this so that you can detect different kinds of networks. So for instance, a corporate network, and so on and so forth, just as a heuristic to give you a good feel for whether you should launch a certain operations or not. Similarly, you might have a scenario where you do have internet connectivity, but you're going through a transparent proxy. And for certain kinds of applications, it's important to know whether there's someone in the path between you and your final destination, whether you're being proxied. And the way to solve that, the way that the Network Location Awareness Service solves that problem is we send a request for a known URL, and if we get the response we expect, then we know it's the internet. The other thing that we also do is that we also look at the time to live that we get back on multiple requests, and if they're all the same, going to multiple destinations, we know that by definition someone must be terminating this connection and then proxying us out without our knowledge. So this basically restates what I just mentioned. The fact that this is a built-in capability means that it's much more scalable, and multiple applications on the same system can take advantage of the basic capabilities. The other key thing about this is that it works for both IPv4 and IPv6, which is a key point because IPv6 is enabled by default in Windows Vista. I'm sure many of you have heard, and your level of connectivity may differ between IPv4 and IPv6. So for instance, for IPv4, you might have only site local connectivity. You might not be able to receive connections from the global internet, whereas your IPv6 connection may be able to receive connections from the global internet, and vice versa. So it's important to be aware and cognizant of what level of connectivity do I have, what kind of environments am I in, and to have that logic built into the core networking stack itself, which is what we've tried to do with the network location awareness capabilities. So second big challenge. Another thing that happens with IPv6 is that you have a lot more addresses than you had with IPv4. Right? IPv6 has link local addresses. It has site local addresses that have been deprecated, but you still have global addresses, and you may have dozens of, link local and global addresses on any given machine. So the question arises, if I want to connect from, point A to point B, which of these addresses do I use? If you think about what that works out to, you have this PC, again, is associated with a hotspot as well as having a plugged-in connection. The hotspot address has its own address. The hotspot interface has its own addresses, and then the wired connection has its own addresses, and then the server that it's connecting to has a bunch of addresses as well. So if you try to take the cross product of these, you'll spend a lot of time trying to figure out which one of these is the right connection. The way that we've approached that in the platform to make life easier for applications is that we just provided new APIs, connect by name and connect by list. And these APIs are designed so that you can simply say, I want to connect to the following list of addresses, or I want to connect to the following name. We'll go off and resolve the name. And then underneath the covers, we'll try and optimize the connection establishment process, looking at information from a variety of sources. Currently, what we do is that we just simply try one combination at a time. This is another area where we'll be doing additional work in the future to make that a lot smarter, and to also allow you to put in security parameters. So for instance, saying I want to connect with the following security